Today we're going to talk about parent functions. By the end of today, you'll be able to recognize graphs of parent functions given an equation or a graph, and be able to describe the domain, range, and end behavior for each parent function. Let's start by matching the names of the functions to the equations. Some of these should be pretty obvious, others you might not remember. So the easiest one should be a linear function, and that is equation E, y equals x. Others are pretty intuitive. For example, A, you have y equals square root of x. That is a square root function. F is y equals the cube root of x. That's a cube root function. D, you may or may not remember that those bars mean absolute value, so that is an absolute value function. And then the last two, you have a quadratic and a cubic. Hopefully you remember from Algebra 1 that y equals x squared is a quadratic function, which means that y equals x cubed is a cubic function. You need to remember these equations. We will come back to them all year. So we're going to take a look at each of these functions individually, graph them, make a table, state the domain, range, and end behavior. So the first one here is a linear function, y equals x. Now we're going to make a table, even though you don't necessarily need to make a table for this one because hopefully you remember how to graph a line. We're going to do it anyway. I'm going to pick x values that I know will fit on this graph and will give us a good graph of the equation. So I'm going to pick -2, -1, 0, 1, and 2. So if y equals x, that means that all of the y's are the same as all of the x's. So if I plot these points on the graph, I have -2, -2, -1, -1, 0, 0, 1, 1, and 2, 2. So my graph is a line with a slope of 1 going through the origin. Now, we talked about domain, range, and end behavior a couple classes ago. So if you look at this equation, remember domain is how far to the left does the graph go and how far to the right does the graph go. There's an arrow at both ends of this equation. So on the left side, the graph will continue toward -infinity, and on the right side, the graph will continue toward +infinity. And remember that if you're writing this in set notation, you would write this x such that x is an element of the real numbers. Range, we look at how low the graph goes and how high the graph goes. So again, since there's an arrow at the end of this graph, it will continue to go down to -infinity. And the arrow at the other side of the graph means that the graph will continue to go up toward +infinity. And in set notation, this would be y, because we're talking about the range, such that y is an element of the real numbers. And now for end behavior. Remember that you always start off the same way for every end behavior. You say as x approaches either positive or -infinity, f of x approaches blank. So if we look at this graph, this first statement says as x approaches negative infinity, which means the left side of the graph, that is going down, so it's approaching negative infinity. The second statement says as x approaches positive infinity, so we're talking about the right side of the graph. That arrow is pointing up, so it is going toward positive infinity. So this is the basic linear function, its domain, range, and end behavior. We'll look more in depth at these graphs next class. So let's take a look at the next graph. We have y equals absolute value of x. This is an absolute value function. You probably have never seen the graph of this function, but you will see it a lot this year. And again, I'm going to choose x values that I know will give us a good picture of this graph. So I'm going to choose -2, -1, 0, 1, and 2. Absolute value means that you're looking at how far away from 0 the number is. So -2 is 2 away from 0. -1 is 1 away from 0. 0 is obviously 0 from 0. 1 is 1 away from 0. And 2 is 2 away from 0. So absolute value is distance from 0. And you will notice, based on this y column, it's always positive. So if I plot these points, if -2, 2, -1, 1, 0, 0, 1, 1, and 2, 2. You'll notice that this graph is V-shaped. You need to remember that. So if we look at the domain of this function, on the left, the graph continues on forever. On the right, the graph continues on forever. So the domain is -infinity to infinity, or in set notation, x, such that x is an element of the real numbers. For the range, the lowest that this graph goes is right here at 0. So the lowest it goes is 0. The highest the graph goes, both of these ends will continue up toward positive infinity. So the highest the graph goes is positive infinity. So in set notation, that's y such that y is greater than or equal to 0. And then the end behavior, as x approaches negative infinity, f of x approaches, and as x approaches positive infinity, f of x approaches. So if we look at this graph, both the left and right sides of the graph are pointing up. They are both going toward positive infinity. The next graph, y equals x squared, is a quadratic function. You should have seen these toward the end of Algebra 1. I'm going to pick x values, -2, -1, 0, 1, and 2. Now, this says y equals x squared. So -2 squared is what? It should be positive 4. Because remember, squared means that you multiply something by itself. So -2 times -2 is positive 4. So -1 squared is -1 times -1, which is positive 1. 0 squared is 0, 1 squared is 1, 2 squared is 4. So I'm going to go ahead and plot these. Now, I actually have room on this graph to fit a couple more points. So I'm going to go ahead and add -3 and +3 to my x values. -3 squared is 9. +3 squared is 9. So I can add those points. So this graph is U-shaped. It's very important that you make a distinction between the shape of an absolute value function and the shape of a quadratic. An absolute value function is V-shaped, a quadratic function is U-shaped. This shape is also known as a parabola. So the domain for this function. If you look at this graph, on the left side, the graph will continue going on forever, so it'll go to -infinity, and the right side will continue going on forever. So the domain is -infinity to infinity, or in set notation, x such that x is an element of the real numbers, or all real numbers. The range, the lowest that the graph goes, again, is 0. The highest that the graph goes is infinity. So this is very similar to the absolute value function. And in set notation, it's y, such that y is greater than or equal to 0. And then end behavior. If you look carefully, both the left side and the right side of the graph are pointing up. So both of these are approaching positive infinity. The fourth equation is a square root function. And these are tricky. When I am picking my x values, I am going to purposely pick the points or the numbers that I know are easy to square root. So I'm going to pick all perfect squares for my x values. So I'm going to pick 0, 1, oops, not 2, 4, and 9, because those are all perfect squares. So if I plug these into the equation, the square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3. Now, notice that I did not pick any negative x values. Can you take the square root of a negative number? No, or at least not that you've learned. We will learn later that you can take the square root of a negative number, but it's kind of a special circumstance. So for now, you cannot take the square root of a negative number. So I'm going to plot these points. And since we just said that you cannot take the square root of a negative number, I'm only going to put an arrow on the right side of the function. I cannot put an arrow on the left side of the function because I can't say that this graph continues onto the negative side because I just said you can't take the square root of a negative number. So if we look at the domain of this function, the farthest to the left that this graph goes is 0. The farthest to the right that it goes will be infinity. Or in set notation, x such that x is greater than or equal to 0. The range, the lowest that the graph goes, is 0. And this arrow will continue going up, but very slowly, but it will go all the way to positive infinity. So the range is y such that y is greater than or equal to 0. Now for the end behavior, I'm only going to write one part of the end behavior because I only have one arrow at the end of this equation, or the end of this graph. So I'm just going to write the end behavior for the right side because that's the only side that has an arrow. So as x approaches positive infinity, f of x approaches, now technically this is pointing up, so that approaches positive infinity. Since we don't have an arrow on the left side of the graph, we just have a point here, I cannot write the end behavior for that side of the function. Graph number 5 is a cubic. Again, I'm going to pick x's that I know will work, so I'm going to pick -2, -1, 0, 1, and 2. And then if I plug those numbers into the function, -2 cubed is -8, -1 cubed is -1, 0 cubed is 0, 1 cubed is 1, 2 cubed is 8. So I'm going to graph these points. So the graph of a cubic function is this kind of squiggle. And it does need to be rounded, not jagged. For example, this is not right. Do not draw your graph like that. It needs to be smooth. So the domain of this function, on the left side, this arrow will continue going out to the left, so it will eventually get to negative infinity. And on the right side, this arrow will continue going to the right, so the domain is negative infinity to infinity, or x, such that x is an element of the real numbers, or all real numbers. The range on this side, the lowest that the graph goes, will be down to negative infinity. The highest that the graph goes will be infinity. So the range is y, such that y is an element of the real numbers, or all real numbers. So let's write the end behavior. So the first statement says as x approaches negative infinity, so that's the left side, that arrow is pointing down, so it's approaching negative infinity. And then on the right side, the arrow is pointing up, so that is approaching positive infinity. The last graph we have here is a cube root function. Now, I need to think what numbers can I plug in for x that will be easy to take the cube root of. So I'm going to pick -8, -1, 0, 1, and 8. The cube root of -8 is -2. The cube root of -1 is -1. Cube root of 0 is 0. Cube root of 1 is 1. Cube root of 8 is 2. If you notice that that is just the reverse of the table for the cubic function. These are called inverse functions. We'll get more into that later. But if you remember that the cubic and the cube root have pretty much the same tables, just the x and y are switched, it will help you remember those tables better. So let's plot these points. And again, this graph should be a smooth curve, not a jagged graph. So the domain here, the farthest left that the graph goes will be negative infinity. The farthest right that it goes will be positive infinity, or x, such that x is an element of the real numbers. The range, the lowest that the graph goes, this left side of the graph will continue going down, so it will eventually go to negative infinity. And the right side of the graph will continue going up toward positive infinity. Oops. So the range in set notation would be y, such that y is an element of the real numbers, or all real numbers. And then the end behavior. So the first statement as x approaches negative infinity is the left side. This arrow is pointing down. And then on the right side, the arrow is pointing up. You need to memorize these graphs. And you don't necessarily have to memorize their domain, range, and end behavior, but you need to be able to figure them out. You will have a quiz on this, and you need to make sure that all of these points on the graphs are exact. You cannot just draw a squiggle and say that that is a cubic function. The points need to be precise. So make sure you practice these and memorize those tables.